Hello everyone, my name is Vassilis Nikolaidis and I'm an assistant professor in the Department of Electrical and Computer Engineering at the Democritus University of Thrace in Greece. In this slide you can also see the co-authors of the paper. According to the IC standard EN 50160, the permissible limits for supply voltage variation are plus minus 10% around the nominal voltage magnitude for 95% of the week. Distribution system operators take different measures to achieve this goal. Among the most frequently applied ones are those measures shown in the bullets here. In this work, we focus only on tap changer and demand response operations. In order to control the distribution voltage, we propose to enable the automatic online tap changer operation on the medium voltage, low voltage power distribution transformer of the distribution system. Keeping, of course, the automatic on-load tap changer operation of the bulk high voltage, medium voltage power distribution transformer as well. We further consider that the consumers of the distribution system are participating in a demand response program that allows the utility to shut down part of the electrical consumption during peak loads in exchange of an incentive. Moreover, we consider voltage protection of DG units because although DG protection is important for the integrity of the DG unit itself, from the viewpoint of the distribution system operation, if there is an unintentional trip of a DG unit, this of course deteriorates the system operation. The control strategy is based on threshold-based voltage criteria, and it is fully decentralized since the only requirement is our local voltage measurements. The test system used in the analysis is the 20 kV overhead power distribution system shown in this figure, based on realistic data received by the Hellenic, the Greek distribution network operator. We assume aggregate loads connected, supplied by the medium voltage and low voltage buses. These aggregated loads comprise residential and industrial consumers. The daily normalized active and reactive power demand profile for the residential and industrial users are shown in the bottom of the slide. We also consider DG production. In particular, we assume controllable diesel generators and uncontrollable PV units. For the PV units, we took this active power production profile for the PV units, as I said. We studied 4 different cases. The 3 first cases assume 0 DG production. In case study 1, only the main transformer regulates the voltage in the system. In case 2, also the medium voltage, low voltage distribution transformers are left to regulate the voltage. In case study 3, demand response is also applied. Finally, in the case study 4, this production is also assumed, and all the examined measures are in operation, in action. The base case, which is case study 1, is the case where only the main transformer regulates the voltage. As we can see in the first figure on the top of the slide, this transformer changes the tap changes on this transformer regulates is sufficient. These tap changes are sufficient to keep the voltage in the secondary bus within the deadband. However, in the figure on the bottom, where we see the voltage evolution of all the medium voltage buses, we can see that for the remote buses, there is a violation of the lower permissible voltage limit, which is 0.9 per unit. This is even worse when we analyze the voltage of the secondary buses of the remotest transformer. Let's say, for instance, in this figure on the right, we see the secondary voltage of the remotest transformer, and we see that it reaches very low values. In case study 2, the medium voltage, low voltage transformers are also left to regulate the voltage. This measure alone is not sufficient to restore the voltages within the permissible limits. But of course, all this voltage profile is increased, the voltage profile is improved. The combination of the operation of the LVC of the medium voltage, low voltage transformer with demand response actions is the measure that the voltage control measure that brings the voltages in the normal operation area. However, we can see that there is an amount that is set from the consumers. In the case study 4, we assume a DG production. Of course, when DG is connected to the network, voltages increase, but even though the DG production assumed in this case study was not sufficient to bring the voltages within the permissible limits, and therefore demand response is also necessary in this case, but it is significantly lower than in the previous case. We can see also a different example where we assumed that at hour 9, a DG unit is unexpectedly tripped due to an internal fault, and this brings all the voltage profile throughout the distribution system to lower values. We see that the voltages at some buses drop lower than 0.9 per unit. But what we see is also that the voltage at this bus, at bus 5, drops below this limit, 0.88, which is the under voltage threshold for the voltage protection of this unit. Therefore, the unit connected to this bus is also disconnected due to the under voltage protection. You have two successive DG unit trips, and however, even though the combined operation of the transformers with demand response actions also succeeds to keep the voltage within the permissible limits. So, distribution voltage control strategy is proposed based solely on automatic voltage operation and demand response. It is a fully decentralized scheme. It is shown that the proposed method efficiently controls voltage within the permissible distribution levels, but there are some points for the future. We have to investigate these points in the future. For example, we have to optimally decide the voltage thresholds and the demand response amount, and of course, you have some preliminary investigation already made, where we saw that the number of tap position, if we increase the number of tap position from 2, which is the typical for power distribution transformers, to 4 or 6, let's say, then a better voltage control is achieved. Thank you.
If there are any questions.
Yes, I have a question. Thanks for your presentation. Especially the case study was great. I just wanted to ask, maybe I have missed it during the presentation, how did you conduct your simulations? Did you solve some model? Because
yes.
What I was asking myself is how these tap ratio settings are basically, how do you come up with these specific tap ratio settings like at specific points in time?
So we used Simulink for this.
Okay.
Okay. And we modeled the difficulty there was to model the time varying loads. We used the dynamic programming load. It is a block from Simulink,
Okay.
which we inserted, entered in table format the load consumption for each specific time, for each specific hour.
Okay.
And this was also made for the generators. The generators were negative dynamic loads of the model.
And okay, so which means Simulink could decide which ratio or like which setting to give to the tap to the transformer. Like it was something that Simulink could decide.
Yes, there is
Okay,
a model,
yes. Yeah, okay.
online tap changer model in Simulink.
Okay, yes.
But we had to modify this model because the
I
model
understand.
had a specific, a certain tap ratio band,
Thank you.
let's say, and we modified this in order to adjust it to our analysis.
Thank you.
Do you consider any controls on the distributed generator?
No. We just entered the production according to the generation profile.
With unity power factor?
Unity power factor, yes. Because we suppose that the producer wants to maximize the benefits.
I just have a quick question. What demand response is being done apart from the tap changing?
The demand response, because we have low voltage problems in these cases, was to set the load from the customers.
Okay, you said just
To set down a part, not all the customers, but a part, a percentage of the consumers. Yes.